It is now my pleasure to introduce Professor Koroush Shirvan from Massachusetts Institute of Technology, or MIT. Now, Koroush specialises in the development and assessment of advanced nuclear reactor technology in the Department of Nuclear Science and Engineering at MIT. He's currently focused on accelerating innovations in nuclear fuels, reactor design, and small modular reactors to improve the sustainability of current and next generation power plants. His approach combines multiple scapes, physics, and disciplines to realise innovative solutions to the highly regulated nuclear energy sector. He is also the co-director of the Nuclear Reactor Technology course for utility executives. He is the 2022 recipient of the Reactor Technology Award given by the American Nuclear Society. Can we please welcome Koroush to tell us, how does nuclear energy work?
Oh, great. Yep, thanks for the introduction, and thanks for University of New South Wales as well as this workshop for hosting me. So I was given a kind of an introductory talk on how does nuclear energy work. I think one slide that I can really summarize this is this one. So a lot of you probably hear about nuclear energy, think something extremely advanced, extremely complicated. In reality, it's basically a steam engine. And I've been told Thomas the Train is very popular in Australia, so hopefully you can relate to it. And what it does, it fundamentally, all nuclear reactor technologies, they take this nuclear energy and transfer heat to water, they boil it off, create steam, and have that steam run a turbo generator. That's all the nuclear power plant, whether it's on a submarine or on land, that's how they generate electricity at the end of the day. And it generates this electricity in a very carbon-free manner. In fact, the International Panel on Climate Change, as well as other studies, have repeatedly shown again and again, when you account for life cycle emissions, including mining of uranium that happens a lot in Australia, all the way to the end electricity generation, is going to be one of the lowest carbon means that you can produce energy today. And it also runs in a very dispatchable manner. As you all know, when you look at alternative clean energy like solar and wind, they depend on weather. And with nuclear, it really does not depend on it. As long as you have enough fuel on site, you can basically run this forever. So when you look at your overall energy grid portfolio, with wind and solar, without any help of storage, once you go above 30% or so, you're going to have that storage infrastructure. You're going to have this additional infrastructure. Versus with nuclear, theoretically, you can actually go all the way to the 100%. We have empirical evidence in France where they have gone to all the way up to 80% of their total electricity generated by nuclear as one source, because you can actually bring these things up and down and have a reliable grid. So what does it look today? So if you look at from the 1980s all the way to today, nuclear has been consistently producing same amount of total energy. Today it's around roughly just under 10% of the world's electricity. And what's interesting to see, here's the nuclear in the green, is that all the retirements has basically been counteracted with new nuclear power plants coming online since the 80s. But the fossil, even though we've discussed all these climate change concerns and future of a low carbon world for the electricity sector, you can see that fossil fuels has gone up. So in order for us to really reach let's say a low carbon future, we have to utilize all these energy sources that produce low carbon in a much more significant way. And when you look at what produces that 10% of world's electricity, it's about 440 reactors. And out of that 440 reactors, has been basically roughly last 20 years, 100 new reactors coming online and 100 reactors retiring. And when you look at, what are these reactor types, you can see that most of them are of this pressurized water reactor technology. So for the remainder of my slides, I'm going to focus on this PWR technology because that's the most reactors that are out there. And this is also the basis for nuclear submarines and nuclear carriers that you guys in Australia are looking at. And on the military side, outside of 440, we have about 160 military ships composed of 200 smaller reactors, since you don't need as much power on the sea. If you look at this breakdown, the second most popular reactor type is the boiling water reactors. A lot of them were in Japan. And the pressurized heavy water reactor, a lot of reactors in Canada, and as well as India. And then you got some gas-cooled reactors in UK, and then the fast reactors in China right now are being constructed in China as well as operating in Russia. So when you look at what is being constructed today, by overall majorities, again, pressurized water reactors. So that's why we'll just focus on explaining that. The other thing that this plot shows on the number of reactors that are being constructed today is that the world continues to build large water reactors, mainly pressurized water reactors. A lot of times when you look at media, and I've talked to a lot of politicians in the US, the impression is that China or Russia are building every type of reactors out there, and they're doing a lot of crazy things. In reality, as you can see, is pretty much everyone is building that, including as well as China. Outside of the PWR, all of them are large. 2 of them are actually small, also known as small modular reactors. And the 2 small pressurized water reactors, one is being built in China and one is being built in Argentina. So the pressurized water reactor, as the empirical evidence show, is the past, present, and the future, at least for the near term, next 20 years, that's all the plans are. So let's dive in to see what it actually, how does this technology work? So when you look at a couple of pressurized water reactors in California, comparing them to the nearby solar thermal plant, also in the state of California, you see the massive difference in the amount of land that the 2 PWRs are taking compared to the neighboring solar thermal plants. And in this case, they're producing over 2 gigawatts of electricity. Here, they're producing 400 megawatt electric, but at the quarter of the time, whenever the sun shines, versus here, they can theoretically produce beyond 90%. And so that ends up with having a much lower land use for nuclear compared to other technologies. Now, this capacity factor, which is the percentage of energy generation out of a year that a plant would operate, these are generic values. And so a lot of times when we compare technologies to other technologies, we tend to use generic values, but in reality, it's very important to get actually what is, let's say, how much solar you actually get in Australia, in the south of the country versus the north of the country. So that becomes very important to not think about electricity production generically. So what does that look? So if you take these 2 plants, put on a map of where we are, you can see they would basically take this much space. Versus if I put that solar thermal plant and just increase it to a point that I get same amount of electricity generation, it would take a lot more space. So this is my second time ever coming to Australia. I don't know how many people actually live in this area. You probably know it. Now, a lot of people may say that, listen, this is great, but if I put these 2 next to population zone, you're probably gonna get a lot of, you need a lot of the people that live around there get petition signed, got to go through that different from local, state, all national government to make this happen. Versus this one, it takes a lot of space, but what's next to here? Can someone help me since I'm not from here? Eventually you get the desert. So why don't we just like in California, why don't you move that in the desert and bring the power in, right? So I can do that, and desert population density is low, so maybe you don't care about land usage in desert, right? Well, these 2 plants that generate 6% of electricity, we can actually also, if you're really worried about putting it next to a population zone and impacting the thermal output that the reactor does to the ocean, you can actually also put it in the desert. And in fact, we have few reactors in the middle of a desert in the US. These are the Palo Verde nuclear station in Arizona. Arizona has very much similar climate as the desert part of the outback part of Australia. And so the way it is they literally built 3 reactors in the middle of a desert, and the water that's used to actually reject heat and cool the reactors on the power side is actually wastewater. So what they do is they take wastewater from the very populous cities in Arizona, bring it in, and they use that. So it's here would be basically Sydney. Anyone use water here in this city? Yes, so you can take the wastewater, bring it in, make an artificial lake, and use that to cool the reactors away from population if that's needed. And what's amazing about these 3 reactors is that, again, very low land usage, but very high power. So 3 reactors total, we're talking about 4 gigawatts of electricity. And that's about, I think, greater than 10% of Australian electricity. 3 reactors in the middle of the desert. So you replicate this like 6 times, you get 60% nuclear. And the other thing is that this is actual data now, not the generic data. They operated past 10 years, on average 93% of the time. And that coincides to 32,000 gigawatts hours of electricity. And that is tremendous amount of energy coming from a very, very small area. And one of the things that actually happens in the US is that because California has done a lot of solar and wind generation, they have a lot of intermittency. They buy their power from this generation in Arizona, which is situated right south of California. So let's study this reactor in the middle of a desert more closely, of seeing what each part is. And by the way, this reactor took about 10 years to construct when it was back in many decades ago. So let's start by this side of the picture, the turbine building. Later on, we'll talk about the reactor side and the reactor itself. So what is the turbine building? So the turbine building basically works with pressurized steam. Again, just like the Thomas engine, you create the steam, you run the engine, in this case, a turbo generator. And roughly, because of the properties of water, we're limited to roughly 300 degrees Celsius. So this steam is about 300 degrees Celsius, and it's pressurized in order to have enough energy to move the turbine. Now, just like the name suggests, a pressurized water reactor, it's not the boiling water reactor. The water that goes inside the core is also just liquid water. It's not boiling when it goes inside the core. But in order for me to generate steam from this water, I use the steam generator to transfer heat. And because water boils at 100 degrees Celsius at normal pressure, I have to make my pressurized water reactor, where the water cools the nuclear fuel, all the way up to about 150 times the atmospheric pressure, so that it doesn't boil at 300 C when it rejects the energy to the turbine island. So the pressurized water reactor, I have to actually go to 150 times the atmosphere, pressurize it in order for the water to stay in the liquid form. The other feature of this is that out of the energy that the nuclear side generates, about only a third of it gets to electricity. Now, when you look at thermal power plants, which is basically power plants that use heat to boil water and use a steam turbine, this was basically roughly the performance back in 1970s, whether it was coal, gas, or nuclear. Since then, there's been a lot of advancement in how they take heat to electricity in other sectors. So in combined natural gas plant, they have a steam turbine as well as a gas turbine. They have both of them. And so they're able to get 66% efficiency. And that's one of the reasons why you see, when you look at the capital cost of a nuclear power plant compared to a, let's say, combined cycle gas plant, the capital cost always will be higher no matter what, because they're able to take twice more efficient in producing from heat to electricity, versus we're limited to this because water, if you look at the diagram for water, the maximum temperature we can go is 370 C, because beyond that, water becomes supercritical, and there's that's a different type of reactor called supercritical reactor that has never been built because there's a lot of materials challenges associated with that. Now, in a modern pressurized water reactor, this side of the house makes no impact on the safety case. So in fact, all the new reactors, as well as reactors that have been recently come online, like the AP1000 in the US, the vendor, the nuclear vendor, does not have to even define what is in the turbine island. So the new scale small modular reactor that was recently licensed by the US nuclear regulator, they have no schematic of what is the turbine island. It's just something that shows up in the graph. There's nothing, because it's nothing to do with the nuclear safety. And that's going to be always all the reactors that come online in the future. Now, moving on to the nuclear island, you see these two big compartments. Let's go on the left first, the auxiliary building. So what is that? You can see there's some pumps here. It says low pressure safety injection pump. There's valves, piping there. So what are they? So one of the unique features of the nuclear power plants, and no matter what type of nuclear power plant you have, we're talking about fission power plants, not fusion power plants, is that once when you shut down the fission reaction, you always are generating heat. This heat comes from the byproduct of fission that we'll talk about later. And so it's always generating heat. So if you always generate heat and never cool, what happens? I just keep generating heat. I don't cool it. Just gonna get hotter and hotter and hotter and hotter to what happens? It's gonna melt, right? Eventually, you can't even produce gases. And these are materials that are radioactive. So what we need to do is we need to cool it at all times. So that's what the auxiliary building does. Pumps, valves, pumps in water in there to make sure we always cool this reactor at all times. And that's why it becomes highly regulated, to make sure that these things work. So you see multiple one of these. So we have like multiple pumps, multiple valves, multiple piping, very independent and diverse set of means to ensure that the fuel is always cool. And these are in traditional existing reactors as well as some of the new ones. They're all basically powered, all these things are powered by diesel generators. Because you can imagine if in case of an accident or something happens, there's a blackout event, you can't rely on the reactor itself to generate power. So you use a diesel generator as a backup. And so what happened at the Fukushima accident that you all probably have heard is that the tsunami took away those diesel generators that powers all these systems. So if it takes them away, what happens is the fuel's gonna get hotter and hotter and it's gonna have a partial meltdown. Now, when it does that, does the radioactivity just come in and escape to the environment directly? No, we have this containment building, which is a reinforced structure containing this. Right? And we'll talk a little bit more about it. Now, we've in the US, just literally a few weeks ago, we had our second advanced pressurized water reactor, AP1000, connect to the grid. And that reactor actually works a little bit differently than this safety system I'm showing you. So in that case, instead of having all these pumps and valves and piping and all these redundant systems, they actually go ahead and move tanks of water above the reactor. So they move basically these tanks of water above the containment building. And then, so if you have a heat up event, then you naturally cool the containment by just throwing some water over it over a period of time. And this water inventory in the AP1000 is good enough that it lasts for 3 days. So for 3 days, no operators, nothing has to happen in order to remove this heat. So in case of Fukushima type incident where a tsunami comes in, there is no diesel generator for it to flood or batteries for it to damage. It's just you have basically tank of water that naturally just moves it in. And they reinforce this such that if there's an airplane craft crash here, it's resilient to it. If there's a strongest earthquake in the last 10,000 years ever recorded, it's resilient to it. So that's how it works. And so it's able to remove the heat. So you can see here, once I shut down the nuclear reaction, I'm going to have 6% of the power produced from that decay heat. That's the heat that I said that never goes away. Remember, again, one of these reactors can produce few percent of electricity in Australia. So few percent of that few percent is still a massive amount of heat, right, that we gotta remove. But that heat kind of goes away. These radioactive products decay away as it goes on. So you have to remove less and less heat as it keeps going. But still, I need some system to remove it. And so newer reactors are trying to, particularly also advanced reactors as well, trying to remove this heat without the need for these pumps and valves. Now, there is no free lunch here. This sounds like a much simpler, better system, right? In order for this water to actually go in, I had to actually elevate the reactor building by 80%. And also, it's made out of a steel containment. Now it's a standalone steel containment. That tends to be more expensive than a reinforced containment. So there's savings from one side of removing the pumps, but then there's added cost on the others. All right, so what does this having all these safety systems mean for nuclear compared to other sources? So if you look at all the data and pretty much from various organizations, there's no really, I would say, a debate on this, that when you look at number of deaths that nuclear has caused and other energy sources have caused per energy generation, so death per megawatt hour of electricity, nuclear is among the lowest. It's similar to wind and solar. And that basically is thanks to all those safety systems that are there in order to reduce the nuclear hazard, and the containment building that basically makes it very unlikely for anyone outside to be exposed and have a result in a fatality. Now, when you look at people who do in the business of quantitative risk assessment of nuclear power plants for existing reactor, we use a metric called core damage frequency, but it's basically a probability of having a Fukushima type event. And we've had this type of analysis for decades, and that shows that all the reactors, technologies that were built before the 1980s, every 20 to 30 years, we should expect a Fukushima type event. And in fact, if you look at the history, we had the 3 Mile event, and then we had few reactors Fukushima. This math works out, that every 20, 30 years, we're gonna have this event, which doesn't kill anyone, but causes a massive problem from a point of view of the enterprise. It's tens of billions of dollars to clean up, to recover. It's a huge public perception issue. And so what we've done, and since this analysis has been around decades, all the new reactors, pretty much all the new reactors, some still building some exact old version, pretty much all the new reactors come in with higher added degree of safety. These passive reactors, those reactors that just use gravity to cool, they have much even further lower probability of a core damage. So we've designed that such that all the new reactors coming online, replacing this old fleet that was in Fukushima, is able to bring down this probability such that if core and nuclear, the 400 reactors we have today, increase by a factor of 10, they will not have an event for 100 years, which is the maximum lifetime of nuclear power plants. So we built this such that in our lifetime, you will not actually see another type of Fukushima accident. So keep that in mind as we'll talk later on value. So now that we talked about the safety system, this containment, let's dive into the reactor vessel, this thing over here that's generated. So all the heat that's generated in nuclear is actually just from this component here. So theoretically, if you didn't have any of this, nuclear would be much, much more compact. and this vessel, it's a size that you can actually fill multiple, at least 3 of them here on this podium, given the height of this building, and generate. Those are basically the 3 vessels of the Palo Verde plant that generates greater than 10% of electricity of Australia. And so these vessels, you can see they have fuel assemblies here. These fuel assemblies are made out of cylindrical fuel rods. They're about 4 meters in length and 20 centimeters in width, the assembly, and then the rods are about 1 centimeter in diameter. So pretty skinny cylindrical rods. They're made out of a metallic layer, and then inside that metallic layer, hollow layer, we have these pellets. You can see these dark little cylindrical pellets. Now, each of these pellets, that you have about 50,000 of these in a reactor core, is equivalent to 200 gallons of oil or 20,000 cubic of natural gas. So this is where the power density of fission comes from. So why is that so dense? Let me just skip this. It's so dense because the energy of fission is so much more energetic than combusting carbon. So if you look at the fission event and comparing the energy generated per mass for fission, these are different reactors up here, and compared to natural gas, you see that there's a 70,000 times scale difference between combusting fossil fuels than actually having the fission reaction. So that power density really shows up into these pellets. We lose a lot of these power densities because then we have this containment, all these safety systems, the turbo generator, reactor building, the switch yard, all those things. You have that in a power plant. So where does this pellet come from? Well, this pellet comes from starting with mining of uranium. That happens, a lot of it happens here in Australia. And then so you mine uranium and then you convert it to yellow cake. So it becomes a uranium oxide. And you take this uranium oxide and you create uranium hexafluoride out of it because you want it to be a gas at relatively low temperatures in order for you to spin it in a centrifuge. So when you get this uranium from the ground, only less than 1% of it is actually material that we can fission in a reactor to generate energy. And so when we're spinning this gas, we're able to increase the concentration of this material that actually fissions, which is the uranium-235 isotope out of the uranium element. And so once we get it in the desired amount of enrichment, then we turn it back to an oxide, in this case uranium dioxide, and we form these pellets. So these pellets are ceramic oxide pellets. And these pellets are what they have on the average 3 to 4% of that fissionable material, U-235, in them, that actually fissions and gives us that 70,000 power density versus fossil fuels. Now the fission process, the way it works is that a neutron comes into that uranium-235 nucleus, and there's a probability of different reactions happening, but if the fission reaction happens, what happens is that it transmutes to a different isotope and then eventually splits into 2 other isotopes. So in a nuclear reactor, you basically have the entire periodic table in one side because you're converting, you're creating things. Back when it started, people actually looked at using nuclear reactor to generate gold. How many people like gold? So they were like, okay, well, neutrons can basically transmute one element to another element. When we use that, then you have to deal with all the radioactive material. It turn out to be too expensive. But people now, there are actually companies looking at taking rare earths or platinum, things like that from already existing spent fuel. And so you have these fission products, and the slowing down of these fission products in that UO2 pellet is what generates the heat in the pellet, and then the water runs outside of these rods and cools them up. So the pellets gets heated up, water comes in, cools it off, transfers the heat to the steam generator. Then you generate steam and run the turbo machinery. So what's the implication of this is that these products are radioactive. So we have to always maintain them inside the nuclear reactor and all those barriers of the cladding and the vessel and the containment and everything. And that radioactivity, which means it just gives out energy, that's what produces that decay heat that never shuts down. So we always have to cool it. But what's nice thing about them is that because they're so large, they can only travel the length, almost the thickness of your hair. That's how far they travel. So they're all contained in this pellet. They don't go anywhere. And that's fundamentally why in fission it's so much easier to produce energy than fusion. Because in fusion, in the most way that people pursue using deuterium and tritium, which is basically hydrogen atoms, what happens is that all the energy is actually carried by neutrons. Neutrons are tiny, they're light, they can zip through meters away, so you have to try to capture them meters away from your source. Versus in fission, these things move, again, thickness of your hair, so you can locally remove them here. That's fundamentally why it's so much easier, and why nuclear fission is always going to be more compact than a fusion power plant. All right, so we have this power density, so that means that the waste or the spent fuel that the power plant generates is going to be also very small in quantity just because of this high power density. So This is a nice pamphlet online. I encourage you to look at more detail of it, because I think it summarizes a lot about how much waste is out there. Out of 10%. So if you look at this, 10% of world's electricity is from fission, and that means that every 10 years you basically fill up a football field at a 5-meter height every 10 years. I understand in Australia rugby is very popular, right? How many national rugby teams are there for this one? I don't know. Roughly. Dozen teams? Or, a dozen teams, let's say. So a dozen team, you can put, if you look at that for 100 years, you can basically use those fields to store all the waste out of fission if you want to power the entire world with a fission. So we're talking about very, very small space. All right, so that's how that PWR technology on nuclear works. Now, a few slides on the history of this. So the history of pressurized water reactor. So this technology was really made for the submarines that you guys are going to get. And that's what's going to be there. And it was in the 50s that was initiated. So we have really over 70 years of experience with this technology. And you can see why every country is pretty much gravitating towards this, because it's something that's proven. So what does that look like for a submarine? Well, again, same idea. I got the reactor, my primary circuit where the containment building was, and then I got my turbine island, turbo machinery there. Except here, instead of electricity to homes, electricity to a impeller. that's the only difference. Now, there are a lot of talks about smaller of these water reactors called small modular reactors. And fundamentally, again, same type of layouts. The idea is the same. In this case, this is the reactor. In this case, they move the containments, become steel and very tightly containing the reactor vessel here. And again, you have a pressurized water going in, transmits heat to a steam generator, produces steam, and steam comes out, runs the turbo machinery. Same idea, just a different arrangement of things. And out of this, both in the US and internationally, all these small modular water-cooled reactors are all also PWRs, except for one, which is the BWRX-300 by GE Hitachi, and this is a technology that Ontario Power Generation Canada looking to build. Right now they're in the process of licensing this technology. But they've already started some site preparation. Some of these plants actually don't even use pumps to operate. So all reactors today, over 400 reactors today on land, as well as the 200 reactors in the sea, they all use pump for the water to move and cool the core. Some of these reactors actually eliminate that part to make basically even less potential for a loss of a pump event. What about non-water-cooled reactors? So there's also a whole soup of advanced reactors. Now, as you saw, no one's really building them. These are still things that are conceptually being designed. But what they are mainly is that there are basically technologies of the past. I gave a lecture on advanced reactor to the AUKUS course that Professor Bongiorno organized at MIT. And when I was middle of my lecture, one person raised their hand and said, okay, lecture title, Advanced Reactors. Every time you introduce an advanced reactor, you say that a prototype or a commercial version was built many decades ago. Okay, so where is the advanced reactors? So fundamentally, the advanced reactors have no innovation. They're just bringing back the technology of the past into current, and we'll talk about why that is. Some examples. So this one is actually a reactor that's operated in China. You can go to beyond 300 C. You can go to for steam, you can go to 550 C. And with that 550 C steam, you can maybe do beyond just spinning a turbine, generate electricity. Maybe you can support some chemical processes. The Russians are building a lead-cooled, liquid metal-cooled reactors. And with this reactor, what it does, you got more neutrons to actually transmute more of the spent fuel. So bring the footprint lower, the time that it takes for that radiotoxicity of the spent fuel lower, or to create more fuel out of it, breed more fuel. So there's these technologies that are out there. And one thing though, that the smaller size water-cooled reactor and the non-water cooled reactor give you is this. I mentioned, putting those two reactors in very close to this city will be very controversial. There's also an emergency planning zone where you got to work with the local authorities in case of a Fukushima type event. But what these reactors allow you to do is there is no more evacuation zone. So the Nuclear Regulatory Commission for the water-cooled new scale small modular reactor, because the power rating is smaller, so that means you have less radioactivity, they've already approved their methodology to have no evacuation zone for their reactor. So this thing can really able to integrate it better with things around. I think the last slide, so why those advanced reactors are not advanced today, why there's no innovation. All these companies started with innovation. The best example is the traveling wave reactor supported by Bill Gates, this company called TerraPower in the US. They started with this idea of a traveling wave, which travels, the wave is actually a burning of a nuclear fuel over time to get, and you don't need enriched fuel to refuel it. It can last for a long time. But then what happens is customer says, I want your reactor in the next 10 years. Government says, I'll give you money, and I'll only give you money if you build it in the next 10 years. What do? They have to go back and propose the exact same design for the nuclear island. So what they've done is they've adopted the 1980s GE PRISM design as the nuclear island design. And the reasons being that new fuels, new type of reactors, which use innovative reactors that use materials, takes 20 to 30 years to qualify. So you have to use those legacy ones if you want to meet the demand now. That's not to say that in 20, 30 years, you can work on something, but the issue is what happens all the time. Customer wants something in the next decade, and for nuclear to be licensed and constructed, everyone has to revert back to what's been shown. So what are solutions to a lot of these? Is that, well, first, you don't need advanced reactors to produce electrons. You got the large reactors that people are building. The second one is, again, going back to those plots, right? Nuclear is already the safest, one of the safest forms of energy. I showed you that we made it even 2 orders of magnitude safer in order for it to flourish in the world and not have a Fukushima event in its lifetime. How safe is safe? Because every time we add this, what happens is, based on very strong empirical evidence, that's what has caused nuclear to have higher cost of deployment. So we have to really look at, can we have performance-based regulation, not regulation that hinders its commercial outcome. And then the last one is that we really need established R&D capabilities. We'll have a workshop, I think, tomorrow here. It's all about how to do this, and to do this you need like research reactors, you need test reactors to test these materials, because without them you can't really do that. And so the R&D sector really needs a strong support. So with that, I'll end. Again, how does nuclear work? It generates steam. That's all it does.